Bismillahirrahmanirrahim. Assalamu alaikum. In our today's lecture, we shall work on the Regula-Falsi method. You will find different names of this method. Another name of this method is the Regula-Falsi method, and might be you find some other name in literature. First of all, as usual, we shall be describing the theory or the procedure of this method, and at the end, inshallah, we'll be solving an example. So without wasting any time, let's start the procedure of this method. The title of the method is Method of First Position, and another name of this method is, the most common name of this method is the Regula-Falsi method. Okay. If you have gone through the previous video on the bisection method, this method also works almost on the same lines. So here we take start with a function, say f of x is a function whose root we are looking for, and the domain in which the root lie is a and b. Okay, and for the time being, we assume that the function is having a positive value at a, and at b it is suppose having the negative value. It depends upon the nature of the function, but for the theory point of view, we have taken these two informations. And further, you can see here the product of these two values of the function at a and b will be negative. So this is the condition which describes or tells you that the root of this function lies within this boundary of a and b. So in other words, we have to always fulfill this condition before selecting a part of the interval and rejecting the part of the interval. You'll see in few minutes. So here you can see we have taken the function value is positive at 0 and function value at b is negative at 0. If I describe all these informations through a graph, suppose a is here and we have a positive value of the function somewhere here, okay, for this reason. Similarly, we have the other endpoint b, and the corresponding value of the function is negative, and it will be definitely below the x-axis. Now we assume that the curve of the function which joins these 2 points is looking like this. Okay, so this is the function's curve which is joining these 2 points, and here you can see the curve is crossing the x-axis at this location, and this is the basically the exact or actual root of the function which we have to approximate by using this method of Regula-Falsi. So first of all, if you look at it, corresponding to this point a, over here the coordinate of this point, if I call this as the point A, so the coordinates of points A are, the x coordinate will be A and the y coordinate will be the value of the function at A, and this is f of A. Okay, and similarly corresponding to the point B, the x coordinate will be B and the y coordinate will be f of B. Okay, so here you can see we have described 2 points a and b having coordinates a f of a and b f of b. Now if we approximate the root of this function f of x, which is shown here through a graph, by using the straight line. Suppose this is the straight line and this is your first approximation for the root of the function, and here you can see the straight line crosses the x-axis at this location, and we can label this location as say x1. Okay, so here the straight line joining these 2 points meets the x-axis at x1. So x1 is going to be your first approximation for the root of the function. Actual root is somewhere here, but this is the first approximation. And the Regula-Falsi method proceeds if we draw a perpendicular from x1 which meets on the curve at some point, and this generates one more point on the curve. Now if I join A once again with the point, with this point, with new point, so you can see here the line joining these 2 points is now crossing the x-axis at a better location compared to the x1 location. So I can label this as x2, and similarly you can call it as x2. Okay, here let me show it. And similarly, if you want to further furnish your route, we draw one more perpendicular from this location and joining this point once again with this new point. So here you can see again and again, whenever you proceed, each time your approximation is getting closer and closer to the actual route. And the process will be definitely keep on going unless we reach to the required accuracy of the route. So this is the graphical way through which we get the idea how actually Regula-Falsi method proceeds. Now we have to add some mathematics. In order to add mathematics, I use the first line, the line joining the points A and B. Here this is the line I'm talking about this. If I want to write down the equation of this straight line, A and B, joining these 2 points A and B, we can write down the equation of the straight line by using the format y minus y1. If I label it as, say this is your x1 and y1, and this is your x2 and y2. And we know the formula. Okay, how actually we can write down the equation of the straight line by using these 2 points. The y minus y1, y1 is f of a over y2 minus y1. Okay, so this is the left side of the equation, and the right side is x minus x1, which is a. You can see x1 we have labeled it by a, and x2 minus x2 is b minus a. So this is the equation of the straight line joining the 2 points A and B. This idea should be clear in your mind how actually we construct this equation of the straight line. The formula for the 2 point formation is y minus y1 over y2 minus y1 is equals to x minus x1 over x2 minus x1. So I have used this format in order to write down this equation of the straight line. Now, if you look at this first point, whenever this line joining the points A and B meets the x-axis at this location of x1, so you can see here at x1 location, the y coordinate of the straight line will be 0. And the x coordinate will become equals to x1. So here you can see we have y as well as x. So this y will be 0 whenever we are at this location of the x-axis. So here the equation now takes the form minus f of b a whole divided by f of b minus f of a, and this is equals to x will be replaced by x1 and a over b minus a. Okay, so here we have put y equals to 0 and x equals to x1. Why did I put y equals to 0 and x equals to x1? You can add this statement here. Okay, at the location of x1, at x1, in other words, the coordinates of this point will be, of course, x1 and 0. So x coordinate will be x1 and y coordinate will be 0. So x will be replaced by x1 and y will be 0. So y has been eliminated. Now you have to solve this equation for this x1. So whenever you solve it, you will be getting a result which I am writing here directly. Okay. So we take start from here, and we are now going to solve this equation for x1 on taking out x1 on the left side and shifting all the other quantities on the right side. We will get a times f of b minus b times f of a and f of b minus f of a. After small manipulation, you will be getting this result, and it is not very complicated. Okay, after noting this, so this becomes the formula that will give you the first approximation for the root of the given function in the form of x1. Let me show it all on the straight line, as we have been showing in the case of the bisection method. Excuse me. So this is the left hand point and this is your right hand point. Here we have assumed the value of the function is positive, and here we have assumed the value is negative. Okay, and the condition of the product of these quantities negative holds here. And now by using this format or formula, we'll be finding this x1. Whenever you use this formula to find out x1, this is not compulsory that x1 should be the midpoint of the a and b. This point can be anywhere in between a and b. But it may be exactly the midpoint, but it is very rare. But generally it can be anywhere within the domain of a and b. So for the time being, we assume that we have somewhere x1 like that. This is x1. And further, after finding x1, the next step is to calculate the function's value at x1. Okay, and whenever you find out the function's value at x1, function which is given to you in the beginning, so you will be using that function and putting this value of x into that function, and you can get the output. The output can be having three possibilities. Either the value of this function can be positive or negative, or it can be 0. If it is 0, you are at the root. There is no need to go ahead. But whenever it is other than 0, so then of course we have to proceed for the better approximation. So here f of x1 for the time being we assume is negative. Okay. Actually it will depend upon the nature of the function, but for the procedure point of view or the theory point of view, I am taking it as negative. So here I show it that the function is having a negative sign at x1. And now we have two parts of the domain. You can see one part starts from a and goes up to x1, and the other starts from x1 and moves to b. So these two parts are there, and out of these two parts we have to discard one of the section. And how do we decide which part we have to keep and which we have to discard? It depends upon the same principle that we have to select those two endpoints where the function will be having opposite signs. So whenever we make the comparison, so here the function is having positive sign and here it is having the negative sign. So this means that this is the most suitable interval where the function is having opposite signs. If you look at the other part of the interval, both are having the same sign. So this indicates that this section of the domain is going to be discarded from the whole domain. So the new domain will be now from a to x1. And how actually we write it? So here we write it as the product of the function at a and the function's value at x1 is negative. This holds the condition. Therefore, the root therefore the root of the function fx lies in the new domain, and the new domain is now a to x1. So here you can see the domain has been squeezed. Initially it was from a to b. Now we have discarded a section from the domain and the interval is now a bit smaller compared to the previous interval. And till here your first iteration completes. And now to proceed to the next iteration number 2, and we can call it as the iteration number 1. For the iteration number 2, you have to proceed all these steps once again. We'll be using this formula once again, but now you have to be careful that the interval has been changed. The formula will also be changed. And now we show the next approximation by x2. Previously we have shown it by x1 and now we show it by x2. Okay, and here you can see a is still intact. There is no change in a. but the value of b has been replaced by x1. So where there are b, we have to replace it by x1. So the formula takes the form a times f of x1 minus x1 f of a whole divided by fx1 f of a. So here you can see the formula is slightly different from the previous one because the domain was different. Here the domain is a new one, so the formula will be, of course, not the same. Now whenever you make all these calculations, you will get some value. Then at this value of x2, once again you go in search of x2, the function values at x2. And again there can be three possibilities. Either it can be positive, negative or 0. So for this time we assume that this is positive. Okay, we are just assuming it. In actual, whenever you are solving the question will decide either it is positive or negative. So here whenever it is positive, let's show all these on the new interval. The left hand point is a, the right hand point is x1, the function is having a positive value at a and having a negative value at x1. And we got one more point, and this point will be, of course, within the domain of a to x1. And suppose the point is somewhere here. Okay, and you can see here the function's value at f of x2 is this time is positive, and now we have to decide which part of the domain we have to keep and which we have to discard. So this will be done on the same principle. Okay, we have to check the two endpoints where the function is having opposite sign. So it is quite obvious. Okay, here at x2 and at x1, the function is having opposite sign. So this will be the new domain for your next iteration, and this part will be now discarded. So here we write down as the product of the function at x2 and fx1 is negative, and therefore the root of f of x lies in the new domain of x2 and x1. And one more important thing is that you have to keep the order of these numbers as they are appearing on the interval. Do not change the order. You have to keep the order intact. So till here you complete the second iteration, and you can proceed for as many iterations as you require for the required accuracy of your question, unless you get the accuracy, otherwise you have to keep on going. Now the question arises, these kinds of procedures or these kinds of methods generally looks never-ending process. So where we have to take stop? If you have seen the previous lecture on the bisection method, there we have discussed how we can take the stop of the method. So here we shall be using the same principle. Whenever we are at the level where for any two consecutive iterations the results are same up to 4 decimal places, then we can take stop. So this is the general principle for the practice point view and for the other points view. So I generally use this. So I will be stopping at the place wherever we are approaching for two consecutive iterations having the same output. After describing all the steps behind this method of Regula-Falsi, so now the time to apply it on a question. So let's start the question. The question is, this is an example, and the function given to you is x cubed minus x minus 11. This is the question, and the domain in which the root lie is 2 and 3. How do we find the domain in which the root lie? I have described this step in the bisection method. Shortly, you assign different values to the function, and wherever the sign of the function changes for any two consecutive values, so those two values will be playing the role of your domain where actually the root lies. So this is the general principle I have used, and I got this interval where the root of this function lies. Okay, here you can see if I place 2 into this part of the function, so you can see here it gives you 2 cube minus 2 minus 11, so this gives you minus 5. And similarly, if you substitute the values at 3, the result is equals to 30. So here you can see the sign is negative and the sign is positive here. So these two indicates that these are the endpoints where we have the change in sign for any two consecutive inputs. So this is the domain in which the root lies. So after doing this, the whole work, the next step is to take start of the iteration. Iteration number 1, you have to memorize the formula which we had just derived. The first approximation, we show it by x1. The formula was, if you remember, a times f of b minus b times f of a whole divided by f of b minus f of a. So this is the formula we have derived just now, and now we are substituting all those values. So here you can see a is 2 and b is 3. You can put here a and b just to keep the process smooth. So here 2 times f of b. F of b is, here this is f of b, which is equals to, let me write it here so that you get no confused. So we shall be using this value, okay? So here this is 13 minus b is 3 times f of a, which is minus 5, and divided by 13 minus 5, okay? And whenever you use your calculating devices and solve it, you will be getting 2.2778 up to 4 decimal place. And this is your x1, or the first better approximation. Now you have to find out the function's value at x1. So you have to put this all into the function. So this gives you 2.2778 whole cube minus 2.2778 and minus 11. And remaining you can do it by using your calculators. So here we get the output is minus 1.46. Okay, and you can see here the sign of the function output is negative. And we are not taking here negative or positive, it is coming after the calculation. So whatever the sign comes, we have to act accordingly. Now, after making all these calculations, let's show them on the straight line. So this was initial interval from where we have taken start. Here a is equals to 2, b is equals to 3. The function's value at 2 means at a was a negative, that is negative. And here the function value at 3 is positive. And the point we get is 2.2778. It is somewhere in between 2 and 3. So suppose the point is somewhere here, and we show it x is equals to 2.2778. And the sign of the function's value at x1 is also negative. Now, after knowing all these, we have to decide about the part of the interval which we have to discard. So you have to keep the principle or procedure of the method which takes start is whenever we are discarding a section, we have to keep in our mind that we have to choose only those two endpoints where the function is having opposite sign. So as we have selected this part, you can see here the function is having opposite signs. So here you can see at x1 and x3 the function is having opposite sign. So here we write down, let me complete this iteration here. Here you can see as the product of the function at x1, if I write instead of x1 2.2778 and the function value at 3, these two gives you a negative sign. Therefore, the root of the function fx lies in between the new domain, and you have to keep the order. Order means you have to look which one comes first. So here x1 is coming first, so we write down 2.2778 and the other endpoint is 3. So this is your new domain in which the root lies. Till here, this completes your first iteration. Okay, now after doing this first iteration, I do one more iteration for you on this side. Okay, I have, I think it should be clear, everything. Now we proceed for the second iteration. Okay. So here you can see the new domain is now in between x1 and b, this one and this one. So here we write down the next approximation by x2. This is your next approximation, and x2 will be equals to a times, if I replace it by, instead of writing a, we substitute the values directly without putting x1 or anything else. So 2.2778, this is your actually the left hand point of the domain, which is this one, into the function's value at the right hand point, and the function value at the right hand point is 13. So I put it here 13. Then there is a minus sign. If you have the formula in your mind, I write the formula here, x1 or x2, whatever it is. So a times f of b minus b times f of a over f of b and f of a. Formula is the same. Here we are making the change. This a is being replaced by x1 everywhere. Okay. And b is the same. Now we are substituting the values. x1 is this quantity 2.2778 and fb is 13. Then there is a minus sign. Now we take b is 3. And f of x1. F of x1 we have calculated, this was equals to minus 1.46. Minus 1.46. And in the denominator is the same f of b, which is 13 minus 1.46. Remaining you can use your calculators and simplify it, and you will be getting the value which is equals to 2.3507. Okay. And after finding x2, the next step is to calculate the function's value at the new proximity root, which is x2. So here we get 2.3507 whole cube, 2.3507 and minus 11. And now you have to use your calculating devices. The net result is minus 0.3612, which is obviously negative. Okay. And now after finding all these informations, let's show all these on the straight line here. I replace all these values here by the new value. The right hand point is the same, so we just change the other two values. The left hand point was x1. This is your x1, which is equals to 2.2778, and the function value at x1 was negative. Okay, and now we got one more point somewhere within the domain, and suppose this is somewhere here, x2, which is equals to 2.3507, and the function's value at x2 is minus 0.3612, which is negative. Okay, now looking at all these informations, let's erase it from here and then we decide which is your new interval. Now we have to choose which part you have to discard. So the principle is the same. You have to select those two endpoints where we have the opposite signs. So here you can see at x2 the function is having a negative sign, and at b we have the positive sign. So this part will be the new domain for the next iteration, and this section now can be discarded from the domain. So here, as we write as the product of the function at x2, which is 2.3507, and the function's value at 3 gives you the negative sign. Therefore, the root of the function lies in the new domain, which is 2.3507, and the right hand point is 3. Okay, so this is going to be your new domain for the next iteration. I hope you can understand all these steps. And one more important thing, if you have observed throughout all this procedure as well as in the calculation of all these results, if one endpoint of the interval gets fixed and the other endpoint starts moving towards the root. You can see here 3 is fixed in both of these iterations, and the other point, which was 2 on the left side, is start moving towards the root. As we have seen in the theory, when I was describing the procedure of the method, so there you have seen the point B starts moving towards the point A. So here the same thing is happening. Okay, one endpoints in this particular method of Regula-Falsi, generally it has been observed that one endpoint gets fixed and the other endpoint starts moving towards the root. Now, after knowing all the information, if we proceed for the next iteration, this was iteration number 2, and if you go for the next iteration, you have to proceed for all these steps once again. So I do one more iteration for you so that you can understand how actually we proceed now. So here we replace all these information we gathered. Okay. So this is your iteration number 3. In the iteration number 3, this is your new domain. So here the formula will be replaced by now. X3 will be on this side. X1, previously this was X1, now this is X2. So this X1 will be replaced by X2 everywhere. Okay. And now you have to put in the values. Okay. X3 will be equals to X2. X2 is 2.3507. This is your X2. FB is the value of the function at the right hand point, and that was equals to 13 minus, and then B times the function value at X1, and the function value at X2 is minus 0.3612 whole divided by 13 minus 0.3612. And now you can use your calculators and you can find out the value. The result will be 2.3683. You can verify it up to the 4 decimal places. And after doing this, the next step, I hope you remember it, you have to calculate the function's value at the new approximated root of the given function. This is cube here, minus 2.3683 and minus 11. And on solving it, minus 0.0856, and once again this is giving you the negative sign. And now if you bring all these information on the straight line, so there will be changing the previous informations. The right hand point is still intact, I keep it as it is. The left hand point was x2, and x2 was equals to 2.3507, and the function's value at x2 is we had calculated this was equals to minus 0.3612, and this was negative. Okay, and now we obtained one more interior point x3. Suppose x3 is somewhere here, and this is equals to 2.3683, and the function's value at x3 is minus 0.085 minus 0.0856, and this is negative. And now you have to decide which part of the domain you have to keep and which you have to drop down. So here once again you can see at these two locations we have the opposite sides. So here we write down the function's value at the new interior point, which is 2.3683, and the function value at 3 is giving you the negative sign. So the domain is now in between the two new points 2.3683 and 3. So till here the third iteration completes, and you have to proceed unless you get the 4 decimal place accuracy. And whenever you proceed after almost 6 to 7 iteration, I'm writing here the result after almost 6 to 7 iteration. At the 6th iteration you will be getting the output is 2.3736, and at the 7th iteration you will be observing the result is equals to 2.3736. So here you have the same accuracy up to 4 decimal places for 2 consecutive iteration at the 6 to 7 iteration. If you have seen the previous lecture on the bisection method, we have solved the same question there, and we got the same accuracy up to after 20 to 22 iterations. So here you can see this has reduced almost 50% labor, and you are getting the same accuracy. So this means the convergence rate of this method is quite high compared to the bisection method. And with all these information regarding to the Regula-Falsi method, do more practice and do more questions so that you can get a firm hold on this particular method of Regula-Falsi. So with this, thank you very much, and Assalamu alaikum.